Okay, so here's kind of the culmination of chapter 7. This is what I want to talk about. Okay, I would strongly urge you to get where you can see this. This is the one really big section that's super important. This is what it all builds towards in chapter 7. So put all phones away, everything away that could be any possible distraction. Scoot up, I would urge you to. It's up to you, but I would strongly encourage you to kind of get a better spot. And I'm just going to go through a bunch of examples of solving radical equations, and there aren't very many rules. I'll just identify the rules for you as we go, and you probably will actually. All right, so for this first one, your intuition is going to be right. What do you think you do? Yeah, good. So these are examples where this is one where we can isolate x, right? And to isolate x, we're going to subtract 4. And so we're going to get, oh, you know what I got to do? I got to save this because I'm going to have 1 sec. Darn it.
You don't teach anything period 1, do you?
What's that?
You don't teach anything first 2 periods, right?
I teach calculus. Yeah. Okay, here we go. So to solve this, first thing we do is subtract 4 from both sides. So I get cube root of x equals -4. Now what? Cube it. Okay. To get the x by itself, I have to undo the x to the 1/3, which I do by cubing both sides, right? Okay, so this is, okay, so I'm going to change colors when I do that for a reason that will become clear here shortly. So we end up with x equals -4 cubed, which is what?
64.
Okay, let's check that. Does it work? If I plug -64 back there, what is the cube root of -64? -4 plus 4 equals 0. It checks. So that's our solution. Okay? All right, let's try it again. Something like this. First step, subtract 4. Okay?
I feel like it's
What do I do? Square both sides. If I square both sides, I get x equals, no, just 16. Okay, you see why it's not plus or minus? It's plus or minus if you square root both sides. Okay, so let's check it and see. If I plug that back into the original equation, I get square root of 16 plus 4 equals 0. That's not true, is it?
But it's the negative power.
Okay, it is the negative, but there isn't a negative. So the answer is no solution. Doesn't work. Doesn't work. And we can see that if we were to graph this thing. Let's graph, for example, this blue. Let's graph the square root of x, and then let's graph the function -4 and see where they cross. Okay, because that's a strategy, isn't it? If I write the graphs of both sides of an equation, the intersections of those graphs represent the solutions of the equation, right? Here's the problem with that. If I graph the square root of x, we know what that looks like. It just looks like that, right? If we graph y equals -4, though, it looks like that.
no intersection.
There are no intersections, right? Okay, make sense? Okay, so what happened? We got an answer, though. We got the answer x equals 16. Where did that come from? If we hadn't checked that, we would have missed this problem.
Is it the other part?
Okay, yeah, the problem with this is when you take both sides of an equation to a power, you change the function in a way that might be helpful, but it might be tricky. Okay? You introduce the possibility of extraneous solutions. Okay, so that's why I've got the luxury of being able to pick my color up here, and I always change colors whenever I execute that algebra step. Whenever I take both sides of an equation to a power, I change colors to denote that we've done something risky there, right? So we know that we've always got to check our results. for these extraneous solutions, and this is one. X equals 16 is an extraneous solution, meaning extra, that's doesn't work. Okay?
So how'd you get it if it doesn't work?
It doesn't work because we plugged it back into the original. We have to go back to a step prior to where we took both sides, in this case squared both sides, and see if it actually works, and it doesn't. It's the process of squaring both sides that caused this extraneous solution to occur.
Okay, so what is the answer?
So the answer is no solution. Because the only, and let me make sure everybody understands why. We only got one solution to this equation when we squared both sides. If that doesn't work, there are none. Okay?
So there's
Okay? Now, it's possible, we're going to look at an example later today, for example, where when we solve a radical equation like this, we get two solutions. And, what are the possibilities? Either they're both extraneous, one is a real solution, the other one is extraneous, or they're both good solutions. But we'll have to check them to see each time. Okay?
So for this one, we have to check our solutions every time.
Yes. Anytime you're solving radical equations, that means that you're going to be taking both sides to a power. And so that always means you every time have to check your answers to see if they work. Now, as you do these problems, you'll kind of get some insight and a little intuition. And I knew that this one was going to work. Absolutely knew it was going to work because we cubed both sides, and that's an odd power. And so there are no issues there, right? And you'll kind of get a feel for that. But to play it safe, you should always do that. You should always check your solutions every time. It's not a bad habit to get in anyway, honestly, right? I mean, you want, especially on a test, you should check your solutions to know if you got it right or not before you hit submit.
But can't we just see that we're using the same rules that we did when we're doing the stuff that we were doing?
What do you mean by that, Jonathan?
So like we can't take an even root of a negative number.
You can't take an even root of a negative number.
When it's hooked up, when it's like this.
True. Okay, so
So
yeah,
if-
but
because it
we
moves the
didn't.
square
But
root.
that one's okay, right?
Right.
Okay, but what about this one then? We didn't. We never did take an even root of a negative number, so it's hard to
Right.
see.
But no, but when we
even
checked
square.
it, we had to take. No, never mind.
Okay, but you probably you could have
You
seen.
can't switch it to.
I see what you're getting at. You could have seen the red flags right here if you were really paying attention, though, right? Because we know that the range, if we're really thinking about this absolute value function, we know that the range of an absolute value function, if A is positive, like in this case, the range would just be all non-negative numbers, right? Right, going back to the last stuff that we talked about, and I don't know if everybody's done that assignment yet, but the assignment about the graphs of radical functions, we would have known that the range is all positive values, and so that's not in the range. And so we can see right there we got some issues, right? But I want you to get to a point where you can't always tell, because sometimes these equations get pretty complicated looking, and they might involve multiple radicals. And so I want you to get this to a point where there's an algebra process that you need to add this to your bag of tools for doing algebra. That whenever you take both sides to a power, you always check the solutions. Just make that something you just always do. Okay, what about something like that? Okay, it is a radical, isn't it?
Divide by 2.
Okay, so first thing, we're going to divide by 2, right? We're going to isolate x. So first step is divide by 2. And we get x to the 3/2 equals 125. Now, there's a bunch of ways we can look at this. We're going to try to boil this down to the easiest process that always works. But there's a bunch of ways we can look at this. First of all, what is x to the 3/2? What does that really mean? What if we write that in terms of radicals instead of rational exponents?
It's the square root.
Okay, so it's square root cubed, right? Okay. So it'd be the square root of x cubed, right?
So the answer would be
Yeah, that's going to be the answer. Good. Now, how do we get that?
cubed root and then square.
Okay, good. So the two steps would be we cube root, right? Both sides. And we get, and that's okay. Now, taking a root of both sides, we know how to do, right? We've done that for ages. It's this other part where we undo the radical part by squaring both sides that's the new part. I don't have to change colors when I take a cube root of both sides. Agreed? Okay, we know how to do that. So we end up with the square root of x equals 5. Now, when I square both sides, I've got to change colors, right? It's when I'm taking both sides to an integer power that things could get weird. So x equals 25, and we got to check it. It works, right? So if we go back up and check that, yeah, it works, doesn't it? Right? If I put in 25 here, the square root of 25 is 5, cubed is 125, check. Okay, make sense? Could we have done that more easily? Could we have done that in one step instead of two? Yeah, we could have, right? We could combine those two steps, couldn't we? Cube rooting and squaring is the same as applying what rational exponent? We're taking it to what power if we're doing a combination of cube rooting and squaring? 2/3, right? The 1/3 part is the cube root, the 2 part is the square. Well, that makes sense, right? Because, I mean, think about what that implies here. That implies that we're going to take both sides to the 2/3. That's completely consistent with our properties of exponents, isn't it? If I take a power to a power, what do I do to the exponents? Multiply what's 3/2 times 2/3. So it makes sense, right? We're going to take both sides to a reciprocal power, right? Okay, this is the way that I'd like you to do it, but you got to be careful with this. You got to be careful. First of all, you know that because the numerator is not equal to 1, we're going to have to change colors, aka we're going to have to check for extraneous solutions. But there's another element here too. Is this are we taking an odd or an even root of both sides? Everybody see it's odd? The fact that we're taking this to a 1/3 power means we are taking odd root. So the properties, so all the baggage that goes with that, we have to consider. When we take an odd root of both sides, do we include a plus or minus? No, we don't. We don't, right? So this, if I get this answer then, this just tells me that x equals 125, no plus or minus, right? Just tells me no plus or minus. I just get x equals 125 to the 2/3. Well, 125 to the 2/3, remember how we do that. That just means a cube root squared. Cube root of 125 is 5, squared is 25. So we get the same answer. We just get it a little more quickly. Okay? We still have to check it though, right? Why do we have to check it?
Because we took a square root.
Yeah, because of that, right? Because there's an integer, we took this to an integer power other than 1, right? That's different than what we've done in the past. Let's just really quickly compare that to the problems that we've done up to now, right? We've done stuff like this. If x cubed equals 125, how do we solve that?
Cube root.
Cube root. So we're taking both sides to the 1/3 power.
It's just the reciprocal, right?
Yeah, now but look, that's a 1 on the top. I don't have to check my solutions. I'm just taking a cube root of both sides, right?
What if the top is, so as long as the top is odd, or it has to be?
Okay, we'll look at an example where the top is odd and the bottom is even in a second. Okay, is that right? Because that's not what we did here. We did, yeah, top odd, bottom even. Yeah, okay. Does that make sense though? You get what I'm saying? Taking a root of both sides does not add extraneous solutions, but taking a root and then taking it to some power does. Okay? Questions on that? All right. Okay, let's try this guy. So what are the steps here? Multiply by 2, good. And that's going to give us x to the 2/3 equals 16. Now let's do this in discrete steps. Let's write this as a radical once, just so you know, so we can see that it works both ways. If I write this as a radical equation, what do I get? Cube root of x squared equals 16, right? And so how do I solve that?
Square root.
Okay, good. Do I need to change colors? No. When I square root though, what do I have to introduce? Plus or minus, yeah. Plus or minus, and what do I get? 4, yeah. Okay, and so I've got two answers there, don't I? When I cube root this then, or when I cube both sides, what do I get?
You'll still have both, you still have plus or minus, because it's,
Ah, you're right. I'm still gonna get a plus or minus, right? I'm gonna get the cube root, I'm gonna get plus or minus 4 cubed gives me x equals plus or minus what?
um, 64.
64. Okay. Why did I have to introduce the red there, change colors?
Because you got to check.
Because I took both sides to an integer power, right? Everybody see that? I did this. The numerator's not 1 anymore, right? So I gotta change colors. Let's check those, see if they work. So if I go back, we'll just go up to the spot right here, how about? Let's take the plus 64, try that. So 64 to the 2/3 is what? 64 to the 2/3 is 16, right? The cube root of 64
4.
is 4 squared is 16, okay? Let's try the minus 64. Okay, so negative 64 to the 2/3.
Still works.
Still works, doesn't it? I'm gonna get back, the cube root of negative 64 is negative
4
4
squared is
squared is 16,
equals 16.
right? Does that make sense? So that works. Now, I want you to be really careful with the book here because the book does this incorrectly. They would say that the only answer here is plus 64, and they're wrong. But they say that all through this section, and so don't use the book problems to study from this part unless you're aware of that. Okay, I guarantee they're wrong too. Because if you graph this thing, if I graph this function right here, x to the 2/3, what does x to the 2/3 look like? The graph of x to the 2/3. If you graph it, it just looks like this, right? And so if I intersect that with the horizontal line, 16, look at that, I get 2 intersections, right? Yeah.
What if you had 2 even, like the even square?
Well, you never would because 2 evens would always reduce, right? Okay. Make sense? So how would we do that one without doing it in one step, right? What we did here, and this is fine to do, right? We wrote it as a 2-step process. We wrote it as the power of a radical. We took the root of both sides and then took both sides to the power that we needed to undo the radical part, right? That's fine. How could we do that in just one step? First step would be the same, right? We'll multiply both sides by 2, and we'll get x to the 2/3 equals 16. Now, how can I do this by taking both sides to one fractional power? What power?
3 seconds.
3 seconds, okay,
Three
yeah.
halves.
So,
But now it's red because
okay, so talk to me about that. That's gonna give me x on the left side, okay? Do I need a plus or minus and why? Yes, I do. How come? Yes, look at that. This is an even root, so I have to have plus or minus, right? Everybody see that? So I'm gonna get the square root of 16 gives me my plus or minus 4 cubed is plus or minus 64. Make sense?
Make that pretty long.
All right. How about that?
By both sides by -2 first.
Okay, so we'll divide both sides by -2. Good.
Equals -16.
Okay.
And then, take this, yeah.
Okay, take both sides to the 3/2.
Wait a second. This is not gonna work,
Okay, it doesn't work. How come?
cause you're gonna get imaginary numbers.
Yeah, because what that's saying is the square root of -16 cubed, right? Everybody see that? What this is asking us to do over here is the square root of -16 cubed. Well, you might think, well, what if we just think of it the other way? What if we think of it as the square root? What if I do the cube first? I can. That would be the square root of -16 cubed. I've still got problems.
Yeah.
Because if I cube -16, I'm gonna get a negative number under the radical. Everybody agree?
No matter how big it is.
Okay, so we can see right away that because this is an even root, we violated one of our two rules for real numbers. We can't take an even root of a negative number, right?
Yeah.
Okay, so the answer is no solution. Okay, makes no real solution, okay? Okay, how about that?
So we -2 for both sides first.
Yeah, we're just, and this is, I want you to see here, remember at the beginning of the year, I was bragging about how that order of operations thing was just all of algebra essentially is based on that? Well, it is, look at this. This is just reversing order of operations and isolating x, right? All we're doing here,
So we get
if I subtract 2,
square
square root of
Okay,
4x minus 7 equals 3,
3,
right?
and then square both sides,
So you got square both sides, what's that mean?
plus or minus. No, not plus,
No.
minus, no. We just get rid of that.
Change colors,
Just color.
meaning extraneous solutions maybe, right? Okay, so
Kind of a pain.
4x minus 7 equals what?
9
9.
plus 7,
Okay, add 7,
16,
divide by 4, and I get,
x equals 4.
okay, question, does it work?
Okay,
Where do we go to see?
up there, so
Yeah.
4 times 4 is 16, minus 7 is 9, square root of that is still, it's plus or minus 3 though. isn't
No,
it?
it's not,
It's not.
it's not. Okay, everybody see that? What is the square root of 9?
Oh,
3.
right, yeah, I can't.
It's not plus or
can't- not
minus
plus or
3,
minus
it's 3. When we get a plus or minus, it's if we're taking the square root of both sides of an equation to solve for x, okay? So if I plug that back in, it checks, doesn't it? I end up with the square root of
4 times 4,
16 minus 9, which
Minus
is equal to 3, right?
minus
Oh,
7,
minus 7.
which makes 9.
Makes 9, yeah. Okay, that checks. Square root of 9 equals 3, check, check. It works. Okay, got it? Easy, right? So all we're doing then is isolating the radical. When we get a radical equation like this, isolate the radical and take both sides to whatever power we need to undo the radical, right? In this case, squaring both sides. But that could have been a cube root or a fifth root or anything, right? Isolate the radical and undo it by changing colors.
That was fun.
Okay, how about that? What if I have two radicals in that form?
So, how does that work? So we divide, no,
Say it again? Okay, what do I have to do first? Okay, yeah, now my goal is to isolate the radical, right? Well, what if there are two radicals?
oh, what if?
In this case, I can isolate them both at the same time by pushing them to different sides of the equation, right?
Yeah, see that.
So we'll
Plus
add 2x.
Plus, we'll add 2.
Now, have I truly isolated the square root of x on this side? No,
No.
but if it's multiplied by 2, that's still easy to square both sides, right? So now we'll change colors and we'll square both sides, and what do we get?
So we get 3x plus 2
What about over here?
equals,
Okay, good, because I have to distribute the 2 to both factors, right? Square both the 2 and the radical.
4x.
So 4x, that's easy to solve though.
Yeah, we don't we just get rid of the 4x?
Yeah, so how about if we push everything to this side, subtract 3x from both sides and get x equals 2? Okay, what do I have to do? Gotta check it. So we'll go back to the blue equation before we squared both sides. Alright, so ignore the red. If I plug the 2 in there, does it work?
So
I get
So we get
square
6.
root of,
6 plus 2 is 8,
Four.
square root, which is 4.
okay, so square root of 8's not 4,
Sorry,
right?
2.
But I'm gonna get the square root of 8
Oh, wait, that doesn't work.
equals
we might-
2 times the square root of 2. Is that true?
Oh, that's still 8. That's square root of 8.
Square root of 8 is the square root of 4 times the square root of 2, right?
That's awesome.
So I get 2 radical 2 equals 2 radical 2, check, it works.
So we like just use ugly radical numbers instead of
Right, you get that? Okay, so here's the coup de grace. Oh, no, it's not. This one, we can still do this one without too much trouble.
Yeah.
What do we do there?
Square both sides.
Square both sides, right? I've got the radical isolated, so if I square both sides, I'm gonna get what on this side?
X squared. X squared plus 16.
No?
Yes.
Yeah.
No, I have to,
14 squared.
nah, hang on now. If I do A plus B squared, what's my expansion?
A squared plus B squared.
Mm-mm. Right?
So plus 8.
Remember that? Those are important, right? Remember those. And remember your rule on this. You can always recreate these. Say what? Say it again.
Minus 8x.
Minus 8x plus
B squared 16.
16 equals 2x. Okay, what about these rules though? How do you remember these rules? This is the Pascal's triangle thing we talked about, but really the two that you use the most often are just the expansion of a binomial squared and a binomial cube. So how do you remember those? There's a really quick and easy way to do that. So a plus b squared equals a squared plus 2ab plus b squared. A plus b cubed equals a cubed plus 3a squared b plus 3ab squared plus b cubed. How do we get that? Really easy. There's a couple of rules that always apply. Remember that the sum of the exponents always has to equal whatever the power of the binomial is, right? Okay, so they have to add to 2. Well, what are the ways that I can take powers of a and b where the exponents add to 2? I can either have all a, which is how I always start. I could split it so a gets 1 and b gets 1, or b gets both, right? So we know we're going to get those 3 terms. There's 3 different ways of slicing up that exponent to add to 2, correct? Okay, the other thing that has to happen is the coefficients have to be symmetrical. In other words, if you walk through this equation from the left or the right, you should see the coefficients in the same orders. Well, look at the coefficients. We've got a 1, 2, and a 1, right? So I see 1, 2, 1 from the left, or 1, 2, 1 from the right. But how do I know the second one's going to be a 2? There's a pattern. The first coefficient is always equal to the power of the binomial. Okay? So if it's a plus b squared, the second coefficient is a 2, guaranteed. Look below, same thing down here. That's a cubed, so the first coefficient is a 3. You see that there's no other way to build this thing, right? If I want to build it so the exponents add to 3 and start with the a and ratchet to the b, doesn't that make sense that it's got to be a cubed, a squared, b to the 1, a to the 1, b squared, and b cubed, right? So I need those 4 terms. The outside coefficients are always 1s. The next one's got to be a 3. If I'm going to be able to walk through the coefficients in the same order from left or right, don't I have to go 1, 3, 3, 1? So using those few simple rules, even if you like in years, if you would never do this course, so you're going to take math all the way through, but what if you didn't take math for a couple of years and you had to remember? That's how you can remember, just build it, right? Those rules allow you to build those expansions, okay? Make sense?
which forgot it, we probably don't remember the rules either.
What's that?
Of course,
Yeah,
we
true,
forgot it,
true.
I don't remember.
That'll never be a problem for you folks, so.
Of course, we'll do math all the
Yeah,
time.
that's right, you'll never not do that. Okay, so let's solve this thing. What do we do? Subtract 2x,
Okay, yeah, this is easy.
so I get x squared minus 10x plus 16 equals 0. Does that factor?
No, back,
Are there magic numbers?
yes.
What are they? Okay, -8, -2, right? So I get x minus 8, x minus 2. Everybody see that? Okay, so what are my zeros? What are the solutions?
That was easy.
X equals 8 or x equals 2. We done?
No, check.
Ah, we got to check them. Good. So we'll go back up to the original and check them. Try the 8. Is 8 minus 4 equal to the square root of 16?
Yeah.
Yes, that works. Beautiful. He gets the green check. What about the 2? Is 2 minus 4 equal to the square root of 4? No.
Couldn't you tell just by doing the first half of that, if you get the -2 on the left side, so when it automatically, it's not working.
You mean right?
When you put the 2 minus 4, you get a -2 on the left.
Oh,
side.
yeah, you're right.
So it
Yeah,
automatically-
because you know the square root's only going to give you a positive answer. Yeah, you could. You're right. Okay, make sense? Okay. All right. The coup de grace. This one is kind of tough. How are you going to do this? I mean, it's not super tough, but
Square both
here's a-
sides. Square both sides.
I have to isolate a radical on it, right? And square both sides. I can't isolate both of these radicals at the same time. I just can't do it. So unfortunately, this is a harder problem than this guy was right there. That was really convenient because I was able to kill 2 birds with 1 stone, mathematically speaking. I could square both radicals simultaneously, thereby getting rid of both radicals at the same time. I don't have that luxury here though. I gotta do one or the other. Now, it'd be a good idea here to do the most complicated one first, which is what's set up. So if I square both sides,
Why would it work?
Yeah.
If you squared both sides,
You
you
just
do
get
the
okay, well, let's do it. Let's square both sides. What do I get on the left side if I square that side? Okay, now what's the right side squared?
25 minus x.
No.
No, it's not.
Yeah, I gotta use my binomial expansion. That's A and that's B,
What?
right? So I get A squared
Oh,
plus 2AB, which is -10 radical x,
oh,
plus B squared.
no way. That's
Right?
horrible.
See that?
That doesn't make sense. How do you do that?
Like, how do you know when to use the expansion?
How do you know what?
Doesn't you use the expansion?
Well, whenever you square a sum or a difference, you're using a binomial expansion, right? You square a sum or a difference, that's the pattern that applies. You see how I got the -10x? 2 times A times B. What's 2 times 5 times negative the square root of x? -10 radical x, right?
Oh, this is bad.
So I gotta do it again. Now I have to isolate this radical, don't I? I'll just isolate that radical term, how about it? Okay? So I'm going to subtract the x's. They cancel, that's kind of nice at least, right? I'm gonna subtract, how about if we do this, right? So we end up with 10 radical x over here. We'll add that to that side and subtract, right? Divide by 10. Square root of x equals 2. Now what? Square both sides.
X equals 4.
So x equals 4.
That wasn't so bad.
It's not terrible. It could have been worse though, couldn't it? I mean, it
Yeah.
could have been,
If
these
the
were
x
pretty
was-
tame.
Yeah, if the x's didn't get rid of each other, then we would have more stuff.
Yeah, it would have been a little tougher. So what do we, if we plug that, where do we plug it back in?
Top one.
Do I plug it into red or blue? Blue, right? The original question is blue. We're trying to find the blue answers. So if I plug this back up here, what do we get? We get square root of 9, I get 3, don't I? So I'm gonna get 3 equals 5 minus
Two.
2.
3. Yeah, simple. It works.
Yeah, that's it, right? So it worked.
Ugh.
Okay, make sense?
I thought you said that wouldn't work at the beginning.
Which one?
So we said that.
Just squaring both sides wouldn't work.
Well, it may not work. It did work this time. Okay. Say what that?
I'd say you said before that it didn't work. Or proving that it didn't work.
What did I say?
Never mind.
Let's move on.
Yeah, so just to clarify here, whenever, now we ended up squaring both sides twice, but, so obviously we're checking the solutions, but even if you square both sides once, you just have to check. You're gonna get solutions by doing that, but they may or may not work. Okay, we had a case earlier where it didn't work. So, yeah,
Like, what would you do if one square worked but the other didn't? How would you go on from there?
well, we got that. What do you mean if one square?
Like squaring it, like, I don't even know what I'm saying.
Well,
Like, if you squared it and that square worked.
like if the red worked but the green didn't?
Yeah,
Okay, that can't happen because the red wasn't done.
Right.
Right? To solve the red, we had to go green.
had to go.
Yeah, I mean, we didn't even have to, I could've left it red, would've been fine.
Yeah.
Right, cause I don't know
Yeah,
why you
just
didn't turn it green. The fact that we squared it again was irrelevant, cause we'd already squared it, we already changed colors, meaning we had to check the solutions. Okay, alright, we good?
Yeah. We have 6 minutes.
Okay,
We made it though.